right, so this is the beginning of chapter 3. And in this chapter, we will be taking a look at polynomials and rational functions. In this first section, we are going to look at what are called complex numbers. If you've ever worked with imaginary numbers before, that's what we are working with in this section. In a pre-calculus class, we typically don't go real deep with imaginary numbers. There's a whole field of math that we could study with imaginary numbers, but we will just be kind of scratching the surface for the purposes we will use them for. So this section will serve as just a brief introduction to imaginary numbers. So the definition of an imaginary number, we call this imaginary number I, and by definition, it is the square root of -1. So I is equal to the square root of -1. If we square both sides of this, if I were to square I and have I squared and square the square root of -1, then I squared would be equal to -1. Well, we can do more with I than just I and then I squared. So I is equal to the square root of -1, which is just I, and then I squared is equal to -1. If I were to multiply by I on both sides of my equation here, say for example, I multiply by I again, then over here I would have I cubed, and over here I'd have -1 times I, which is -I. If I go through that process again and multiply by I on both sides, then I have I to the fourth power. And on this side, I would have I times I, which is I squared. And we know that I squared is -1, and -1 times a negative would be +1. So when we square I, we end up with a real number. When we raise I to the fourth power, we end up with a real number. And we will notice that I to any even power gives us a real number. So translating back and forth from imaginary to real numbers. Complex numbers have a real part and an imaginary part. Generally, we will write the real part first and the imaginary part second. And when we add and subtract complex numbers or imaginary numbers, we add or subtract the real part with the real part and the imaginary part with the imaginary part. These are called complex conjugates, and we will use complex conjugates when we divide imaginary numbers. And in order to simplify imaginary numbers where we have a negative inside a square root, if I have the square root of -b, that's equal to I root b. So for example, if I have the square root of -36, I can rewrite that as I square root 36. And then the square root of 36 would be 6. So this would be 6i. Now, in this first example we have here, I have I to the 23rd power. So one way you could evaluate this is starting here. If we continue to go on through the cycle, I should have mentioned this earlier, but if I multiply by I again, then I end up multiplying 1 times I, and I get back to the beginning of the cycle, just having I. So every 4 powers, it cycles through here. So if I'm evaluating I to the 23rd power, I could count through this. So 1, 2, 3, 4, 5th power, 6th power, 7, 8, 9, 10, 11, 12, all the way to 23. And then my answer would be wherever I land here. The other way you could think about this is I to the 20th power times I to the 3rd power. 20 is divisible by 4, and so that would get us all the way back to the beginning of the cycle. And so this ends up just being 1, and then I to the 3rd power would be -I, so this would be equal to -I. The other way you could kind of think about this is 20, this I to the 20th power is the same thing, do this kind of in another color off to the side, is the same thing as I to the 4th times 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 I to the 4th. That would be I to the 4th 5 times. That would be I to the 20th power. So each of these I to the 4ths is just equal to 1. Well, 1 times 1 times 1 times 1 times 1 is just 1. And then we're left with I to the 3rd, which is -I. So those are a few different ways you can think through I to some higher power. For this next example, we are subtracting complex numbers, and I have 6 minus 8i minus 3i minus 1. That subtraction distributes to both of those terms. I have 6 minus 8i minus 3i plus 1. So the real part with the real part, 6 and 1 would give me 7, and negative 8i and negative 3i is negative 11i. The next one, when we're multiplying here, I can distribute this 7i onto both of these terms. 7i times 2 gives me 14i, minus 7i times 9i gives me 63i squared. Well, we know what I squared is equal to. That's equal to negative 1. So negative 1 times negative 63 gives me positive 63 plus 14i, real part, imaginary part, and that would be my answer. In the next one, we have two terms here. And so I can either use FOIL or I can use the box method that I've used before. And I have 5 plus 4i and 6 minus 7i. 6 times 5 is 30. 6 times 4i is 24i. 5 times negative 7 is negative 35i. And then positive 4i times negative 7i is going to be negative 28i squared. But again, remember I squared is equal to negative 1, so negative 1 times negative 28 is positive 28. So in this case, we can go ahead and combine like terms. We have 30 and 28. That gives me 58. Negative 35i and positive 24i is negative 11i. And that would be my answer, multiplying these two complex numbers. Now, when we are dividing, what we're going to do is multiply by the conjugate of the denominator. So up here, when we saw the conjugate or complex conjugates, I have a plus bi, a minus bi. So the only difference is the sign in the middle. The sign on the a stays what it is. If it was positive, it stays positive. If it was negative, it stays negative. But the sign in the middle, the sign on the I term, changes. So I'm going to multiply by 2 plus 5i, the conjugate of the denominator here, over 2 plus 5i. And again, I'm going to need to use either the box method or FOIL to multiply these out. So I'll do my work kind of off to the side here. On top, I have 7 plus 4i. On bottom, 2 plus 5i. That's 14 and 8i and 35i and 20i squared. So combining those like terms, remember that I squared is negative 1. So this is actually equal to negative 20. Negative 20 plus 14 is negative 6. 8i plus 35i is 43i. And on bottom, I can do a box there as well. And we're going to notice something interesting happen here. I have 2 minus 5i and 2 plus 5i. And we get 4, negative 10i, positive 10i, and negative 25i squared. And we see that this positive 10 and negative 10 end up canceling each other out. So that's going to happen anytime you multiply complex conjugates together. If these are complex conjugates, meaning the first term is the same, last term is the same, sign in the middle is opposite, those two terms cancel out, and then I squared is equal to negative 1, so negative 1 times negative 25 is positive 25. So 25 plus 4 is 29, and now we've gotten rid of those complex numbers. It's just a regular whole number in the denominator, not imaginary. So we can go ahead and write our answer here. Negative 6 over 29 plus 43 over 29i. If we could reduce these, we would need to, but these don't reduce. You could leave it as a whole fraction here. Typically, we will separate it though. All right, looking at the next examples here, I have the square root of negative 27 and the square root of negative 48. So first thing I need to do before I can do anything else is pull the i's out of here. So I can rewrite this as I square root 27 plus I square root 48. And we need to pull out as much from the square roots as possible. So it might be helpful kind of off to the side here to do a factor tree for both of those. So I have 27, which is 9 times 3, and 3 is prime. And 9 is 3 times 3. And then for 48, that is 4 times 12. 4 is 2 times 2. And 12 is 4 times 3 and 2 times 2. So I can go ahead and rewrite both of these as I square root 3 times 3 times 3 plus I square root 3 times 2 times 2 times 2 times 2. 48 is 2 times 2 times 2 times 2 times 3. And now I can pull as much as I can out of my square root. So in order to pull something out of the square root, you have to have 2 of them and only 1 comes out. And I have 2 sets of 2's. So 2 times 2. 2 times 2 comes out. So what I have here then is 3i square root 3 plus 2 times 2 is 4i square root 3. And these are like radicals. I am able to combine these. They both have a square root. The radicand in both of them is 3. The index is the same. They're both square roots. They're not cube roots or anything else. They both have an I. And so I have 3 I root 3's and 4 I root 3's. So I have a total of 7 I root 3's. So for the next one, we have -2 square root -9 squared. Before I do anything, I need to rewrite this. Well, the square root of 9 is 3. And with that negative in there, that'll become 3i. So I can rewrite this as -2 plus 3i squared. So I can do a box, and I have -2 plus 3i. -2 plus 3i, that becomes 4, -6i, -6i, and 9i squared. I squared is -1, so this becomes -9. So -9 and 4 gives me -5, and -6i and -6i is -12i. That would be my answer. And then this last one, again, I need to pull that negative out of that square root, so I can rewrite this as -14 plus I root 12 over 2. Well, 12, factor tree again, is 2 times 6 and 2 times 3. So I have 2 2's that can be pulled out to have 1 on the outside. So that would be 2 times 2 times 3. I can pull a 2 out and 2 root 3. So -14 plus 2i root 3 over 2. Splitting those fractions up, I have -14 over 2 plus 2i root 3 over 2. And this can reduce to -7. And these 2's can reduce here. I cannot reduce inside the square root. So if this was 2, I couldn't reduce those. But I can reduce outside the square root. So that becomes plus I square root 3. And that would be my answer. Flipping the page over, we can also plot complex numbers on the coordinate plane. And these numbers act almost just like a regular coordinate. So what we will have is the real axis and the imaginary axis. And so our points will be like points A, B, with the real part and the imaginary part. So looking at this first example, the real part is 5, and the imaginary part is -3. And so it's like plotting the point 5, -3. So 1, 2, 3, 4, 5, -3. And that's where that point would be. Similarly, I have 4 and or -4 and 1. So -1, 2, 3, 4, and +1. And that's where that point would be on the real and imaginary axis. If I only have an imaginary part, the real part is 0, and the imaginary part is -2. So real part is 0, imaginary part -2. And if I have only a real part, the real part is -7, and the imaginary part is 0. So 1, 2, 3, 4, 6, 7, and no imaginary part. And that brings us to the end of section 1.